Welcome to the deep dive. Today we're tackling, well, it's literally $1 million question.
Yeah, it really is. It's right at the heart of computer science, math, too. P versus NP.
Q versus NP, one of the 7 Millennium Prize problems.
Yeah.
You solve it, you get a cool $1 million from the Clay Mathematics Institute.
Right. But, it's actually much bigger than the prize money. It's about what computers can fundamentally do. Efficiently, anyway.
Okay, so more than just bragging rights and cash, what are we actually diving into today then?
Well, we're going to try and unpack what P versus NP even means. Why is it such a monster problem? And maybe touch on what happens if someone does solve it. The consequences could be huge.
Huge. Okay, to sort of get our heads around it, let's think about searching for hidden treasure. In the ocean, say.
Okay, I'm with you. Treasure hunt.
If someone just gives you a map, X marks the spot, coordinates, checking if the treasure's there is, well, relatively easy, right? You just go look.
Sail to the spot, check the coordinates. Easy peasy.
But figuring out those coordinates yourself, from scratch, with no clues, that feels like it could take forever, just sailing around randomly.
Exactly. That difference checking being easy, finding being potentially incredibly hard. That's kind of the essence of P versus NP.
Gotcha. And we've been looking at a whole bunch of stuff for this, right? Some Reddit threads, which are always interesting.
Yeah, computer science, explain like I did 5, even R math. See how people are grappling with it. Plus more formal stuff, MIT News, Wikipedia.
University lectures from Carnegie Mellon, Stanford, the official problem description from Clay Math itself.
And even some research papers.
Yeah.
One on trying to find exact solutions for these hard problems. Another on using machine learning for Boolean insatisfiability, so a real mix.
Okay, let's dive in then. First things first, this complexity class P, what is that all about?
Right, P. Think of P as the set of problems that a regular computer, what we call a deterministic one, can solve pretty efficiently.
Deterministic meaning. It just follows instructions step by step. No guessing.
Exactly. Like a robot following a precise script. And efficiently here means in polynomial time.
Ah, polynomial time. That
Yeah.
sounds important. What does it mean in, like, plain English?
Well, imagine the size of the problem is n, like n cities to visit or n items in a list. Polynomial time means the time it takes to solve the problem grows reasonably with n.
Reasonably.
Yeah, like n or n squared or n cubed, something predictable. The key thing is it's not exponential time.
Exponential time being the bad one.
Oh, yeah. Exponential is things like 2 to the power of n or n factorial. That blows up incredibly fast. Someone on Reddit did the math for an algorithm taking 2 to the power of x time. Just 100 items would take longer than the age of the universe to compute.
Wow. Okay, so P, polynomial time, good, feasible. Exponential, bad. Basically impossible for large inputs.
Pretty much. That's the general idea.
So what kinds of problems live comfortably in P? Things we do every day.
Lots of fundamental stuff. Basic arithmetic, even with really big numbers. Multiplying, adding, solving systems of linear equations, figuring out network flows, like how data gets routed efficiently online,
Right.
finding the shortest path between 2 points on a map, like GPS uses. Dijkstra's algorithm does that, and it's polynomial time.
Ah, Dexter's. Someone on Reddit was confused about that, weren't they? Wondering if PMP would affect it.
Yeah, saw that. But no, Dijkstra's is already efficient. It's NP. PMP wouldn't suddenly break it. It might mean other harder problems could become easy, but Dijkstra's is fine.
Okay, good to clarify. Any other P examples?
Loads of graph problems, checking if a network is connected, things like that. Lots of building blocks of computer science are NP.
Right. Now, I saw something mentioned in the Clay Institute description. The feasibility thesis. What's that about?
Yeah. The feasibility thesis is sort of a guiding principle, maybe an observation. It basically says that if a problem feels practically solvable, like if we have a method that works reasonably well in the real world, then it probably does have a polynomial time algorithm.
So practical equals polynomial, usually.
Usually. But there are caveats. The Clay description mentions work by Robertson and Seymour on graph miners. They showed some problems are technically polynomial time, but the algorithms involve such enormous hidden constants that they're completely impractical.
So P is our theoretical benchmark for easy, but sometimes even P problems can be too slow in reality.
Sometimes, yeah. The constant factors can matter, but generally P is the goal for efficient computation.
Okay, so that's P now, the other side of the coin. NP. What defines NP?
NP stands for Nondeterministic Polynomial Time. The key idea here isn't about solving the problem quickly, What about verifying a proposed solution quickly?
Verifying, like checking the treasure map coordinates.
Exactly. If someone hands you a potential answer, can a regular deterministic computer check if it's correct in polynomial time? If yes, the problem is an NP.
Okay. And this non-deterministic part, that sounds a bit sci-fi.
It's a theoretical concept. Imagine a computer that can magically explore all possible computation paths simultaneously.
Like splitting itself infinitely.
Sort of. If any of those paths finds a yes answer in polynomial time, the non-deterministic machine says yes. It's a way to define the class.
And how does P relate to NP then?
P is actually a subset of NP. Think about it. If you can solve a problem quickly, in P, you can certainly check a proposed solution quickly too, right?
How?
You just ignore the proposed solution, solve the problem yourself from scratch, which you can do quickly because it's in P, and see if your answer matches the one you were given. That check takes polynomial time.
Okay. So every problem in P is automatically an NP.
Correct.
But the big question is every problem in NP also in P?
That is the million-dollar question.
I saw that Robert Frost analogy on Reddit for the non-deterministic idea. That was quite neat.
Oh, yeah. The road not taken. A deterministic computer takes one road. A non-deterministic one, like the user said, is like saying, I took both because I'm a non-deterministic computer. It explores all possibilities at once.
Yeah, nice. Can you give a solid example of an NP problem, one that illustrates this checking is easy idea?
Sure. The classic one is the Hamiltonian cycle problem.
Okay, what's that?
You have a network, like cities and roads. The question is there a route that visits every single city exactly once and ends up back where it started?
Right, like a tour.
Exactly. Now, finding such a route, especially with lots of cities, seems really hard. But if I give you a potential route,
Checking it is easy.
relatively yes, in polynomial time, you just walk through the proposed route, check that every city is visited exactly once, and that there's actually a road between each consecutive city pair in the route and from the last back to the first. That's a fast check.
Okay, I see. Verification is polynomial time, so it's an NP. But finding the route, maybe not polynomial time.
That's the suspicion. Finding it seems much harder. We can formalize this checking idea a bit more, too.
Go on.
We talk about a checking relation, RxY. X is the problem instance, like the map of cities.
Sure.
Y is the proposed solution, the potential route or certificate. The problem is in MP. If there's a polynomial time algorithm, they can check if RxY is true, meaning does actually solve X. Another example is SAT, the satisfiability problem.
SAT.
Yeah, Boolean satisfiability. X is a logical formula, like A or B, not C. Y is a proposed truth assignment, like A true, B false, C says true. Checking if that assignment makes the whole formula true. That's fast. Polynomial time. So SAT is an NP.
Got it. So SNP is about problems where we can quickly spot a correct answer if we're lucky enough to find one or be given one.
Precisely.
Which brings us to NP-complete problems. These sound like the real heavyweights. What makes them special?
They are. NP-complete problems are sort of the hardest problems within NP. They have two properties.
Yeah.
First, they have to be an NP themselves, so solutions can be checked quickly.
Okay.
Second, every other problem in NP can be transformed or reduced into an instance of this NP-complete problem in polynomial time.
Whoa. Reduced. Transformed.
Yeah, it means if you had a magical superfast solver for just one NP-complete problem.
You could use it to solve any problem in NP quickly.
Exactly. By transforming the other NP problem into your chosen NP-complete one, solving it with your magic solver, and then translating the answer back.
So if you find a polynomial time algorithm for any single NP-complete problem.
NP equal to NP. Instantly. All NP problems become solvable in polynomial time. It's this incredible interconnectedness.
That's mind-blowing. They're like a linchpin for the whole class NP. How do you even prove a problem is NP-complete then? Using that reduction idea.
Yep, that's the main tool. Polynomial time reduction. If you can show how to take any instance of a known hard problem, like one already proven NP-complete, and efficiently convert it into an instance of your new problem, such that solving the new one solves the old one, you show your new problem is at least as hard.
So you piggyback off known hard problems.
Basically, yeah. If problem A reduces to problem B and A is hard, then B must also be hard.
And which problem was the first domino to fall? The first one, proven NP-complete.
That would be SAT, the Boolean satisfiability problem we mentioned. That was the Cook-Levin theorem, a landmark result.
Cook-Levin. Okay, so SAT showed this whole class of NP-complete problems even existed. What are some other famous examples?
Oh, there are thousands known now. The traveling salesman problem, TSP, is a big one.
Find the shortest route visiting all cities.
And returning home, yeah, that's NP-complete. Others include set cover, dominating set, lots and lots of problems involving finding optimal combinations or arrangements, many scheduling and packing problems too.
Let's stick with traveling salesman for a sec. Finding the absolute best route. What's the state of the art for solving that exactly? Not just finding a good enough route,
Well, the naive way is just try every single possible order of cities.
which is n factorial, like we said, explodes way too fast.
Right. Totally infeasible for more than a handful of cities. There's a smarter exact algorithm called HeldCarp. It uses dynamic programming.
And how fast is that? Still exponential.
Still exponential, unfortunately. Its complexity is roughly O2n. That asterisk just hides some polynomial factors, and n still much better than n, but 2n is still exponential growth.
And can we do better than 2n? Like maybe 1.9n or something?
That's actually a major open question. As one of the surveys we looked at mentioned, finding an exact algorithm for TSP, or even the slightly simpler Hamiltonian cycle problem, that runs in OC time, where C is provably less than 2. Nobody knows how to do that yet. It's a
Yeah.
big research challenge.
So even within NP complete, there are these frontiers of trying to chip away at the exponential barrier, even if we don't expect to break through to P.
Absolutely. And the survey pointed out something interesting. The best known exact algorithms for different NP-complete problems have quite different exponential bases. Some are closer to 1.1n, others are stuck near 2n. Classical complexity doesn't fully explain why some are seemingly easier in the exponential realm than others.
Fascinating. There are layers of difficulty even within hard.
There really are.
You also mentioned the partition problem earlier, dividing rocks into two equal piles. Why is that such a good illustration?
Because it perfectly shows the P versus NP gap. If I give you 2 piles of rocks, checking if they weigh the same, super easy, just put them on scales. Polynomial time verification, that's the NP part.
Right.
But finding the way to split the original set of rocks into 2 perfectly equal piles, especially if you have, say, 100 rocks of weird different weights.
Seems impossible.
Well, not impossible, but the number of ways to split them is astronomical.
Yeah.
Wikipedia gave the number for 100 rocks, it's like 6.3 times 10 to the power of 29.
Whoa.
Yeah. Even checking a million possibilities a second would take longer than the age of the universe. So checking is trivial, finding seems incredibly hard. That's NP versus potentially not P.
Okay, that really drives it home, the sheer scale difference.
Mhm.
So let's formally state it again. The PNP question.
The question is simply, is the class P identical to the class NP? Is every problem for which a solution can be verified quickly also a problem that can be solved quickly?
Or are there problems in NP that fundamentally require exponential time no matter how clever we are?
That's the crux of it.
And what's the gut feeling in the community? Where do most experts lean?
The overwhelming consensus, based on decades of failure to find efficient algorithms for any NP-complete problem, is that P is probably not equal to NP.
Probably not equal.
Right. The intuition is strong that finding solutions, creativity, search, is inherently harder than just checking them. Verification, mechanics, but. And this is the huge but.
Yeah.
There's no formal proof. It's still a conjecture.
Just a very, very widely believed conjecture.
Extremely widely believed, yes.
Okay, let's play devil's advocate.
What?
What if? What if someone proves PNP? What happens then? What are the implications?
Oh, boy. The implications would be staggering.
Yeah.
Revolutionary, probably.
Like what?
Well, countless problems in optimization that are currently intractable logistics, scheduling complex systems, protein folding for drug design, material science, many could suddenly become efficiently solvable.
So huge breakthroughs in science and industry.
Potentially, yes. Artificial intelligence would likely take a massive leap forward, as many AI tasks involve solving NP-hard problems. And then there's a big one.
Cryptography.
Yeah. As a Reddit user pointed out, most modern public key cryptography relies on the assumed difficulty of certain problems, like factoring large numbers, which is believed to be hard, likely in NP, but not in P. If P and P, efficient algorithms for these problems might exist.
Meaning encryption breaks.
It's highly likely that much of our current encryption infrastructure could be rendered insecure almost overnight if finding the secret keys is just as easy as using them to decrypt. Well, that's a problem.
Understatement. It implies finding solutions is no harder than checking them. That feels counterintuitive.
It does. It would fundamentally change our understanding of computation and creativity.
Okay, what about the other way? If, as suspected, someone proves PANP.
Proving P is not equal to NP would also be a monumental achievement. It would finally put the question to rest and confirm our intuition about computational limits.
Any practical consequences?
Less immediately disruptive than PNP, perhaps. But it would give us a solid theoretical foundation for the hardness of NP-complete problems. One Reddit user suggested it might even allow us to create provably secure encryption, knowing for sure that certain problems are inherently hard to crack.
That would be valuable too. Now, I saw this weird idea mentioned on Reddit, a non-constructive proof of PNP. What on earth is that?
Yeah, that's a theoretical possibility. It means someone could potentially prove mathematically that a polynomial time algorithm for an NP-complete problem must exist, without actually telling us what the algorithm is.
Like proving a unicorn exists but not being able to show us one?
Kind of. And as people joked on Reddit, even if such a proof existed, the algorithmic guarantees might be something absurdly impractical, like n to the power of 10 million, or with a constant factor bigger than the number of atoms in the universe.
So theoretically PNP, but practically useless.
Could be. Theoretical existence doesn't guarantee practical efficiency. The constants and the degree of the polynomial matter hugely in the real world. Think about matrix multiplication. We have theoretically faster algorithms than the basic one, but they only become practical for enormous matrices due to large constant overheads.
Right, theory versus practice. And we cleared up the Dijkstra confusion earlier. PNP wouldn't break it, it would potentially make other hard problems easier.
Exactly. PNP means problems currently only thought to be in NP, but maybe not P, could potentially join the P club. It doesn't demote things already in P.
Okay, so everyone pretty much thinks PONP, but research doesn't just stop there, right? People are still working on these hard NP problems.
Absolutely. Just because we think there's no polynomial time solution doesn't mean we can't find better exponential time solutions, or solutions that work well in practice even if the worst case is bad.
So developing exact algorithms, even if they're super polynomial.
Yes. Trying to push that exponential base down, like we discussed for TSP, from 2n towards maybe 1/9 something. And as the survey paper noted, we've gotten quite good at solving surprisingly large instances of some NP-complete problems in practice, especially if the data has structure. There's often a gap between worst-case theory and real-world performance.
I saw terms like sub-exponential time and the exponential time hypothesis mentioned too. Where do they fit in?
So sub-exponential time is faster than exponential, but still slower than polynomial. Think something like 2 to the power of the square root of n.
Okay, like an intermediate zone.
Kind of. And the exponential time hypothesis, or ETH, is another important conjecture. It basically states that 3SAT, a specific version of the satisfiability problem, cannot be solved in sub-exponential time.
So ETH suggests that for some core NP-complete problems, we really are stuck with exponential time. We can't even sneak into that sub-exponential zone.
That's the idea. If ETH is true, it sets a harder limit on how much we can improve algorithms for many NP-complete problems. It implies that too narrow, or something close to it, might be the best we can fundamentally do for some of them.
And what about when we just need an answer, maybe not the perfect one, for a real-world NP-hard problem?
Then we often turn to approximation algorithms. These run in polynomial time and guarantee a solution that's within a certain factor of the true optimum. Or we use heuristics.
Heuristics being?
Clever rules of thumb or strategies that seem to work well in practice for finding good solutions quickly, but without any strict mathematical guarantee on how close they get to the best possible answer, or even how long they'll take in the worst case.
And machine learning is getting involved now, too. I saw a paper on that.
Yeah, that's a really interesting development. People are using things like graph neural networks to actually learn specialized heuristics for problems like SAT. The idea is the AI can potentially discover better problem-solving strategies than humans have designed.
How's that working out?
Early results are promising in some cases. The learned heuristics can sometimes solve instances faster or solve instances that older methods struggled with. Though currently, the time spent running the complex ML model might sometimes outweigh the savings in search steps. But it's a very active area.
Fascinating. So even without solving P versus NP, the field is constantly evolving ways to cope with these hard problems.
Definitely. The practical need drives innovation.
Shifting back to the core question, though, the R-math discussions really hammered home just how hard proving P versus NP actually is.
Oh, absolutely. The overwhelming feeling there was humility. One person basically said, don't feel bad if you don't get it. Nobody really gets it fully.
And progress seems slow.
A lot of the big results have been negative proofs, showing that certain mathematical techniques, like specific kinds of diagonalization or relativization arguments, cannot be used to settle the question. We're learning more about why it's so hard.
It also seems deeply connected to lots of other areas.
Immensely so. Logic, combinatorics, algorithm design, cryptography, obviously, and even potentially things like quantum computing. Some wonder if insights there might offer a new angle, though currently quantum computers aren't expected to solve NP-complete problems efficiently either, only specific ones like factoring.
It really sounds like you need, well, a lot of background to even start thinking about it seriously. I think I saw a funny comment about needing multiple PhDs.
Uh-huh. Yeah, someone joked you need undergrad, master's, PhD, postdoc, become a professor. Then you might have a rough idea how to approach PNP. It's hyperbole, obviously, but it captures the sheer depth required. It's not a casual puzzle.
We also had that image, the nested heads with the bomb fuse. How did you interpret that?
It's a great visual metaphor, I think.
Yeah.
The nested heads suggest the layers of complexity, the deep thinking involved, maybe even the self-referential nature of computation.
And the bomb fuse.
That speaks to the potential impact.
Right.
The long wait for a solution, the tension, the possibility that an answer could be explosive, disruptive. Whether PNP or PNP, the final answer will be a landmark moment with huge consequences.
A very potent image for a profound problem. Okay, let's try and wrap this up. Could you give us the quick summary, the key takeaways?
Sure. So P is problem solvable quickly. NP is problems where solutions can be checked quickly. NP complete problems are the hardest in NP, and if any of them can be solved quickly, then PNP.
And the big question is whether P actually equals MP.
Right. Most believe PNP, meaning some problems are fundamentally harder to solve than to check. But it's unproven. Solving it either way would be massive for tech, science, math, everything computational.
And even though we don't have the answer, just wrestling with the question has been hugely productive for computer science, hasn't it?
Absolutely. The concepts developed around PVs, SNP, complexity classes, reductions, the very idea of analyzing computational hardness have shaped the entire field. The journey has been incredibly valuable, regardless of the final destination.
So maybe a final thought for everyone listening. Next time you're faced with a puzzle or a problem where finding the solution feels way, way harder than just recognizing it if someone showed it to you.
You might be experiencing your own little slice of the P versus NP conundrum.
Exactly. It makes you think about the nature of problem solving itself. Well, this has been fascinating, a real deep dive into a fundamental mystery. Thanks for joining us.